Oh man. Hello, man. I almost didn't make it back in time to start stream. So I am in the midst of trying to do about 3 dozen different things at once. So I apologize. Today is a little bit discombobulated. However, so yeah, lots of stuff going on. So the plan is to have this be kind of a little bit of a shorter stream as we move through the rest of this paper. Oh man, I forgot to throw notation or where's my mouse? There it is. Discord. What am I doing? All right, these what I'm doing. So I'm trying to like send the notations to people on Discord as well. https://www.twitch.tv/Baron_the Regal Beagle. Cool. Throw that up there, and then throw a similar thing over Schnur. Awesome. Yeah. Hello? Thought I heard B. Okay. Sorry about that. We were discombobulated. All right. I hope your morning is going more well structured than mine. All right. So, sure. For the plan is to continue this. Yes. Okay. We are here. We have our mouse. Okay. So let's take a look where we were. Right. We were looking at sensitivity metrics, and again, as before, our goal with this is to kind of skip over the specific models that he's using or they're using to try and run their analysis, because we don't care as much. But we do care. Let's see. Develop summarize models in ways that is reasonably complete. right? So we talked about the sensitivity. So how did he do this? Oh right, we're talking. Okay, so relative errors. Oops. In figure 4a, the relative error taken from figure 3 compared to global precipitation relationship. Okay. We may have a dog joining us at some point, so we'll see how that works. I hear the rumblings of a dog next door. Hobby. Poor beef. Okay. Right. So, working towards a reduced set of metrics will require careful consideration of several factors, even when a strong relationship is found between a relative skill, right? It is difficult to decide whether one field should be eliminated or whether perhaps errors of two fields should be combined, right? So you have a lot of the whole point of this is you have a lot of different things that you can measure, but you don't necessarily know the interrelations between the kind of causal network that's generating each of these things that you measure, like temperature or pressure or whatever these things, right? And so some of them are interrelated and some of them aren't, right? And so which ones do you keep and which ones do you throw out? Another question of interest is whether it is really necessary to consider a full seasonal cycle. Okay, would the relative merits of models be evident simply by considering the annual mean and spatial distribution of each variable? In 5b, we show how the average absolute change in model ranking depends on whether it is based on the global pattern of deviations from the annual mean or the annual mean pattern itself. The results are mixed. And this is actually something I'm finding too, right? If I do something like a deseasonalization, say, some things change a lot and some things don't. And so what does that mean that I need to take into account? In many cases, differences are small, but there are numerous instances where they are very large. In other words, relative model ranking, in some cases, strongly depends on whether the annual mean or deviations from the annual mean are considered. So what he means by rankings is effect A is more important than effect B, right? So which one influences your final output more? Is it the temperature? Is it the pressure? Is it the relative humidity? Blah, 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 right? All these things influence the result of your model, but which one has the most influence, right? Because ideally you'd want to rank that 1 to n and then take the most important ones and throw out as many as you can to try and simplify everything down. Okay. Plus, it tells you something about the physical causal connections, right? If temperature is more important than relative pressure, then maybe temperature. There's something about temperature that matters more. There's some physical effect in there that you need to take into account. Okay, this is not always sufficient to merely consider the annual mean climate. Okay. We next explore several additional factors that might affect the metrics used here to characterize model performance. 1, simulation of initial conditions. 2, spatial scales considered. And 3, the period of simulation evaluated. We'll see where it goes with this. We might be able to skip over this part too because it might be disconnected from what I'm doing, but multiple realizations differing only in their initial conditions are available for some models considered here and are critical for many studies, particularly those in which initial variability of climate system is of interest. We now focused on a single realization of each model. And what files we okay. Blah 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 blah. We don't care about the specifics of this. Hi, Mr. Potato Pants. Oh, did you grab that to say hi? Did you grab that to say hi, Mr. Potato? Yeah, I know, Papa. I know, no, that is not for you, buddy. I know you cannot have that. No, no, Bubba, that's not for you. I know, Potato. Good boy. Good boy. Good Potato. I love you. I love you so much, Potato. Yeah, you're a good boy. Good tail wag. Please don't destroy anything. Okay. Uh, yep, you can sniff that. Just don't like try and chew it or stand on it. That's fine. You can sniff it. Anyway. All right. So right, he's talking about variations from based on initial conditions. Please don't stand on that. No, and do not chew. Hey, stop that. Potato, you can sniff, but please don't chew. This dog is nutso. Potato. Patationes. Yeah, potato. Potats. Potatoes. Dog. Woofers. Can you can sniff, but don't bite or stand on. Hey, no, I said don't bite. Nope, nope, nope. Don't bite. Don't bite. Nope. No, you cannot bite it. Potato. He knows that I don't want him to bite it, which means he's going to bite it because it gets him attention. Hold on 1 second. Potato, stop doing that, please. Hey, Potato's going to get you kicked out of the room. Ooh, who's that? Was that Mommy? Did you hear Mommy downstairs? Yeah, right. Yakety Sax is currently playing in my head. I will be right back. I'm gonna just go ahead and give K2 he needs his medication, and unfortunately B is still in recovery mode, so is not able to give him um, his meds. So that will also help. So let me turn this up here. We're just gonna throw up a text. Yeah. BRB chasing potato. Yeah, we'll just go with BRB chasing potato. And we'll change this to block. Ah, shoot. What am I doing? This. Here we go. Now we can add it. BRB chase potatoes. Okay, and we go like this, and we go like this, and then we go like this, and then we go like this. And for people who don't know, I'll let them figure it out. Outstanding. Be right back. Okay, okay. Oh, I need to message B the time that Potato had his pill. Give me 1 second. Just go ahead and go ahead and do something real fast here. I am going to. Nope. I just would like to. Okay. Let's see. Potot pill. Oh, is it 10:45? There we go. All right. Excellent. Where were we? Oh, right. I need to get rid of this. We are no longer chasing potatoes. We are now chasing math. Excellent. So let's see here. Here we go. All right. So in figure 6 was to show the results of the precipitation at mean sea level. Okay, so what are we trying to do? Right, so we care about the relative ranking. We don't care about the specific climatology of these models, blah, blah, blah. The choice of reference data set for precipitation can have a moderate effect on the model's relative ranking. Although the difference is small. Okay. This is perhaps okay. Yep. So again, looking at, let's see here. Average absolute cycle ranking, A, variable by variable, and B, the annual cycle versus the mean. So you can see that the relative rankings can move quite a bit, right? Depending on if you're deseasonalizing or not deseasonalizing. And so that's an important thing. If you have an overarching kind of influence, something like seasonality or daytime, nighttime, or pick something like that, right? You have to see which of your variables are tied to that. And how they're tied to it, right? So if you account for that variation, how does that affect which variable is important? Right? And so that's what he's talking about. Okay. Making climatology more sensible for 20-year averaging period. Fine. Finally, considering the target grid resolution, we find, generally speaking, the course of the grid, the better the model agreement with observation, precipitation, this ranking sensitivity of mean sea. Okay. So it also matters how, right? You're the more detailed you're trying to model, the more difficult it is to model. So the more likely you are to be wrong about things. Okay. An overall model performance index ? There would be considerable value in deriving a single index of model reliability. If this were possible and could be justified, the index could be used, for example, to weight individual model results to form more accurate multi-model projections of climate change. So again, lots of times you don't just take one model, you take 5 different models and you combine them together to get an overall understanding of what's going on, knowing that certain models are better at certain things than other things. And so how do you weight which model is more important than other models? That's a whole thing, right? So should be judging what should be weighted more heavily and what should be right. Forming consensus prediction. Although defining an optimal index of this kind is beyond the scope of the study. That's literally why I wanted this. Buddy. Okay. For explanatory purposes, only a, quote, model performance index, MCPI, has been constructed. This is done rather arbitrarily by simply averaging each model's relative error across all the fields appearing in figure 3. Results are shown in figure 7a and figure 7b, with the models sorted by their MCPI. Okay. Oh, let me see what is RMS for prediction. Okay, here's the ordering. Remember we talked about trying to figure out which of these different influences let me see. Wait. No, wait, let me read this again. Model RMS error in the northern hemisphere extra topics for A, precipitation, B means okay. The sensitivity to different analysis choices are shown in different symbols. Standard choice, alternate reference data. Okay, so this is just showing sensitivity. Whoops, sensitivity to different data set. That's fine. Okay, never mind. That wasn't what I thought it was. Okay. For each model, relative error for each variable contributing to the index, also shown in symbols. Not surprising, the MCPI based on multi-model mean and median fields are lower than the MCPI of individual models. The models that fare well by this measure also stand out in figure 3 as the better outliers with large errors. However, even by, quote, better models have a large spread in their variable by variable performance, particularly in the tropics. Also note that the ranking of models is somewhat different between NHEX and the tropics. Thus, combining these two indices performance would result in a noticeable loss of information, right? So in other words, he came up with this ranking method and then says, but it's not good. Thanks, that is super duper uber helpful. I appreciate that. Okay, the average relative error. Okay. Which NCPI can hide substantial errors. See, this is so. Again, this is what's so difficult, right? You're trying to figure out what the best model is to use, but ways in which you try and compare them are necessarily going to be weighting your answer in different ways. And so you have to be very selective with how you make these cross comparisons. The primary appeal of a single index is simplicity, but a single index could lead naive individuals to draw unwarranted conclusions. Yes. The relative value of different models. This is especially true if the index is based solely on climatology of global scale fields, completely omitting any evaluation of the wide variety of modes, capture modes of variability that might indicate whether the models really have captured the physics of the climate system. There is an understandable concern among model developers that a single index used to rank models would prematurely discourage development of new modeling approaches, which might at first appear inferior, but which might more realistically represent the physics of a system and might further work and after further work might produce a better model, right? So yeah, the clarity about goals is important, and you don't want to have people come up with a model, run this single evaluation method, say, oh, no, this model's no good, and then not explore how it might be improved, right? Okay, beyond the mean climate. The focus of this study thus far has been on simulation of the mean annual cycle. While this may be a reasonable starting point, it provides only a limited perspective on overall climate model performance. Here we take a preliminary look at simulating interannual variability by examining variances of monthly mean anomalies computed relatively to monthly climatology. The RMS error is not an appropriate metric for characterizing this aspect of the model performance because there is no reason to expect the models and observations to agree on the phasing of internal unforced variations. So we know there's a random influence on the timing. That's what he means by phasing, right? On the relative timing of these. So since we know the error is random, we expect them to be off. So just doing an RMS isn't going to tell you much because it's going to vary randomly from run to run, right? Or from month to month. On the other hand, correctly matching observed variances does not guarantee correct representation of the modes of variability responsible for variance. So you could coincidentally be correct about something, but that doesn't mean your model is better, right? You need more than just a couple of successful predictions to be able to say that your model is good. In order to obtain a robust statistical estimate of observed variability, we need data available for a period of a decade or more. This constraint eliminates some of the reference data of our earlier comparisons. As a first step, our assessment of model simulation of climate variability, we focus on upper field. Sure, don't care about the specifics of what they're focusing on. After removing the mean annual cycle from each reanalysis dataset, monthly anomalies are computed for the periods of 1980 to 1999. Similar procedure was followed. Okay, sure. Figure 8, which is down here, presumably. There's figure 8. Variance ratios. Okay. Figure 8 depicts the ratio of simulated to observed variance for these regions. Ratios close to unity indicate that the variance of simulated monthly anomalies compare well with the reanalysis, whereas lower ratios suggest there's too little simulated variability and higher ratios imply too much. In other words, I'm looking at how these months are varying year to year, right? And then I'm taking that and seeing if I'm matching the type of, even if I'm not varying in exactly the same way, am I varying to the same degree that I would expect, right? So even though these are random variations, there is within the random variations kind of a span of how far those go, right? So you want to make sure that your random variations are within the same scope of possibility as the real random variations. So that's one way in which your model can be more or less correct, right? If your model is varying far too broadly compared to the real ones, then it's not a very good model. Right. So, okay, the statistics of the multi-model mean field are omitted in this figure because the phasing, again, the timing is going to be different for each of these. Okay, the variance in both reanalysis are comparable as evidenced. Okay, in the tropics and SHEX, the two triangles on each box are more frequently different, indicating larger discrepancies between two reanalyses. This is not surprising since reanalyses are less constrained by observations outside Northern Hemisphere. In other words, there happens to be more and better data in the Northern Hemisphere than in the Southern Hemisphere, historically. So that means your predictions are going to be different, right? The effectiveness of your predictions are going to be different because your models were generated from more or less data, right? The more data you generate your model from, the more correct your model is probably going to be, right? The more accurate it's going to be. In areas of relatively sparse data, the reference data sets are more heavily influenced by the reanalysis model, and therefore the observational estimates of variability are likely to be less accurate. Okay, most models have too little extratropical variability in temperature at 200 HPA. Again, this is an altitude because meteorologists are weird. This may be because the high altitude winter troposphere is well below 200 HPA, and most models have relatively crude representation of the stratosphere. Several models stand out consistently across fields with too low variability in tropics, where others appear to have too much. We can create an exploratory model variability index, MVI. much as we did for the mean climate by arbitrarily weighting each of the variables in figure 8 uniformly to avoid cancellation between excessive and deficient variability. We define the given model M for a given model M and reference data set R as follows, right? So there's there is how he's computing this variability, where beta squared is a ratio of simulated to observed variance, and F is the number of variables, rows of each panel in figure 8, right? So you're taking each of these rows and you're looking at what the variation is, the ratio of variation between the model and the data, and you're plugging it into this to try and give yourself a metric, right? Is there any relationship between how well the model simulates climate and its ability to capture large-scale characteristics of interannual variability? Using our simple indices of performance, we compare each model's climate and variability scale for both northern hemisphere, extratropical, and the tropics. For both MCPI and MVBI, MVI, the lower the value, the better the skill. So the quote better models would appear in the lower left corner in figure 9. So again, he's come up with these two metrics, right? If you remember, we had our climate skill and our variability skill, and so you want to be in this direction, right? So why arbitrarily? So what he's talking about there is in terms of a coefficient, right? So theoretically, what you should do is each of these elements of the sum should have some coefficient alpha sub f, right? And that alpha sub f would be allows you to more effectively kind of model what's going on, but you then have to figure out how you're going to fit those coefficients for each of the fields f that you're looking at, right? For each of the data sets, and so, but in theory, yes, you would want this to be individually weighted, right? That would give you a more accurate representation. But for starters, right, you can start with just saying, all right, all of the alphas are 1, right? So we're going to start with there and see what happens, and then you can move on from that to try and to make a more accurate model or a more accurate metric by having these alphas and figuring out how you're going to solve for each of those alphas, et cetera, et cetera, et cetera, right? So just to kind of show the proof of concept, he's just using alpha equals 1 for all of them because it simplifies things. All right, note for consistency, MCPI values shown in figure 9 are based on the sets of fields used for MVI. For most models, leads only to modest changes in the MCPI. Okay. There is a possibility that the figures in results to 9b might be sensitive to the occurrence of relatively rare events such as El Nino. We can track whether results are sensitive to sampling by a particular realization of climate noise of this kind, analyzing the multiple realizations. Okay. We can find change in results of figure 9, which suggests that our global scale measures a sample size of 20 years, yields a robust measure of each model's performance in... Okay, so the question is... do extreme events massively change your metrics, right? Do these ratings change if some extreme event skews your data for a small period of time, but is an extreme event, right? And so what he's saying is, on the whole, it looks like no. Figure 9, which suggests for our global scale measures, a sample size of 20 years yields robust measure of each model's relative performance in simulating variability. So in other words, your variability is acceptable even under the case of extreme events because you have a large enough data set to kind of push down the relative effects of an outlier. It can be argued that the realistic simulation of the annual cycle might be required for a model to have reasonable characteristics of interannual variability, e.g. to account for the influence of Asian monsoon on ENSO. This is not necessarily inconsistent with the results displayed in Figure 9, but improving a model's simulation of the mean climate is no guarantee its variability will improve, right? So again, we keep coming back to the same thing. I have this climate that's sitting up here, right? If the question is, am I modeling, there are two things that I could model, right? I could model this mean, or I could try and model the variation, right? These are two ways in which I can model it. So improving one does not necessarily improve the other. Right? These are two different things that you're trying to figure out. The results underscore the limitations of mean climate metrics. They may be woefully inadequate for assessing multiple facets of model performance. At this time, it therefore appears that the climate research community is better served by further work to develop a comprehensive hierarchy of model metrics. So don't just take one, take a slew of these metrics and try and figure out how you're evaluating these to assess the spectrum of processes and phenomena considered important for simulation climate. Summary and discussion. Climate model metrics, as described here, are scalar quantities designed to gauge model performance. Defined for this purpose, metrics can be considered with, quote, diagnostics, which may take the form, for example, maps, time series, power spectra, and often reveal more about the causes of model errors and the processes responsible for those errors. There is, for a variety of reasons, growing interest within the climate research community in establishing a standard suite of metrics to characterize model performance. Metrics are usually designed to quantify how simulations differ from observations, and they are generally used to characterize how well models compare to each other. Unlike numerical weather predictions, there are currently no widely accepted suite of metrics for evaluating climate model performance. The greatest challenge in selecting metrics for model performance is determining what phenomena are important to simulate accurately and therefore to know which metrics need to be measured. It remains largely unknown what aspects of observed climate must be correctly simulated in order to make reliable predictions of climate change, right? So this is still an area of open research. So he's just putting out, hey, these are some metrics, right, to the community, right? Here are some ideas, but I'm not saying this is the way we have to go, but this is just some ideas. All right. The metrics used here indicate that models are not all equally skillful at simulating annual cycle climatology and the variance of monthly anomalies. The information provided by our metrics makes it possible for anyone to draw inferences about the relative performance of different models. But here we point out some obvious generalizations. First, the, quote, mean model and median model exhibit clear superiority in simulating the annual cycles of climatology. This conclusion is robust across variables, regions, and components considered. Okay. Second, there are some models that in many respects stand out as superior. In the extratropics, for example, we find that these models' errors are smaller than most found in a typical model by more than 10%. Relative to most poorly performing models, these errors are lower by up to 30 or 40%. In the tropics, these ones are better, right? While quantitative, these conclusions are drawn by looking collectively at a host of variables having a wide range of observed uncertainty. Moreover, each of these, quote, better performing models, we must reiterate the fact that the range of performance varies across variables, the range of performance across variables is substantial, and at least in the tropics, there is little indication that relative mean climate performance translates to how well the models simulate basic characteristics of variability. So again, models are good at certain things, so you have to be very, very careful with how you're evaluating better versus worse. This study has shown that relative performance of these models by metrics proposed here can be sensitive to choice of reference data, internal variability, for example, exhibited, and even resolution of regridded data, right? So, depends what you mean by AI, right? Unfortunately, AI has come to take on a lot of wacky meanings. This isn't like an LLM approach, but you can do something like a and this has been done. You can do something like a what's it called? Or convolutional neural net or something like that, right? So you can do any of these sort of artificial intelligence approaches that learn patterns very effectively. I think what's useful about this, right, is this is how you're assessing the outputs of those models. So the big problem with those types of models, although they can be very powerful, and can highlight patterns that other models just don't see, is that a lot of times they are stochastic black boxes, right? So you don't know exactly what they're doing inside the model. And as a result, it's very difficult to understand why it's doing better at XYZ than other models, or why it's doing worse, right? So yes, there absolutely is a place for machine learning type models. I'll say machine learning rather than AI, right? For the machine learning type models, and those are integrated in. Sometimes they're integrated as subcomponents within a larger model, right? So there's lots of ways you can try and apply those. Those are effective for certain things, and in fact, they can be more accurate. The question is, how are you judging the accuracy of those models versus each other? And then what can those models tell you? And they can, again, so usually the conclusion is a wide range of different approaches are effective. You have to be very, very selective with what approach you're using for what, right? And so that's kind of the 2-bit conclusion from this whole thing. There are a number of ways you can arbitrarily construct a index of climate skill, and we've illustrated one obvious way to do it. With the results, while the results are generally consistent with our impressions gleaned from a large suite of metrics as to which models do relatively well and which do not, we have not demonstrated that, in fact, this metric has any specific value in determining which model might be more reliable in predicting climate change. We note that the, quote, better models score below average on the simulations in some fields, while the, quote, poorer models score above average in some respects, especially in the tropics. Thus, an overall performance index of this kind is a relatively small residual resulting from a large range of scores from which it is based. In other words, if you come up with a single metric of the, quote, best model, you're hiding a lot of variability, right? You're hiding a lot of sins under that metric. Because the component scores are considerable, are to a considerable degree offsetting, it is reasonable but somewhat arbitrary decision to weight each equally. Right, so that weighting, that, remember he said, is an arbitrary rating of 1, but that's actually really kind of a critically important one. A different choice would lead to rather different rankings of models. It's likely that the optimal weighting of individual metrics contributing to a performance index will depend on the application, for example, prediction of climate change versus a study of ENSO. Additional research is needed to determine which aspects of a model simulation can be verified against observations for the most critical predictive reliability. Till then, the use of a single index to gauge model performance is unwarranted and scientifically unjustified. Okay. Okay. I think we could probably call it there. I think that's a good conclusion to come out of this with. So I think what I'll do for our next approach is I'll look at the papers that reference this paper. That's often what you do, right? You start with a paper like this. That's really interesting. This came out in, 2007? Or 2008 it was published. So I'm curious to see what has happened since 2008. So what we'll do is we'll go look for papers that reference this and see where the concept goes, see how it evolves across different areas. I think that would be super interesting. Yeah, and a little bit more of an in-depth process approach to this kind of thing, right? Because you never want to sit on one paper. You want to have a whole variety of papers that are coming together. So, I think this will be super interesting. This is a great paper. It's a really, really neat paper. For us, again, we don't care about the specifics of the climate models that he's talking about, right? Because we're not trying to model climate. We're trying to model ionospheric loss, which is a little bit different. But regardless, fascinating paper, really good. We will, I think we should deep dive a little bit more into this subject area. So we'll find papers that reference and follow on to this paper and see where they go with it. I'm very curious to see how other people take this idea. With that being said, I think I'm going to cut this here. Thank all of you for hanging out with me as we've gone through this paper on a couple of different paper, both the Sunday morning papers and our other mathy research, right? We've sort of locked onto this paper and kept going. Yeah, so thank you for showing up here. I really appreciate it. We do have 4 viewers, so I am going to go ahead and find someone, see if I can find someone to... Yeah. Send those to me. Absolutely. 100%. I'm very curious to see that approach to it too. So let me go over to Twitch and see who else is doing science and technology stuff and see if we can read into them. All right. Browse. Science and technology. Let's see. Someone's doing a laptop repair. What are you? Okay. Temporary interruption. Okay. There's a lot of people doing computer stuff, but that's not really what I wanted to go for. No. Well, as per usual, there's no one really of interest here. So we're not going to raid into anyone because I don't think it really makes sense. So anyway, thank you once again. We are going to leave it there. So have a wonderful rest of your Sunday and start of your week. And we will reconvene on a Wednesday for our next stream. So again, have a wonderful end of your weekend.